talking about how to implement our excitation table design that we did. So this is that same state example we had done earlier, now for the JKs. So I've got kind of two windows here. I've got the excitation table open just so you can see how I do part of the coding inside of the EDA playground. So kind of in the background, you can see I've got my web browser open to EDA Playground. And inside my design module, Model 1, because I had called that same state design Model 1. This one I've called Model 1 underscore JK. I'm only going to do this one, doing it as register transfer level. We already showed how we could do it with a lot of different ones, gates and everything else. So I don't think that's a tremendously difficult process in there. So we'll just do an example with using the JKs. The output that we've got, again, 2 bits of Q, inputs in, reset, and clock. Remember, the order is not important now with the newest versions of Verilog and System Verilog because we just use the dot notation to assign. The big thing for the characteristic table that we've got is these parameters here. Because for JK tables, you can see I've got this kind of always at pos edge clock and neg edge of reset. You can see I've got this set up. For JKs, I have to actually have, um, using the JK, and I've got 4 states. So I do this as a case statement. That's one way you can do the design for it. And so, I've got, if you look over at the characteristic table, hold is JK is 00, right? So um, I assign the parameter hold to be 2 bits of 0. Reset 01, if you look over the characteristic table, reset is JK is 01. JK10 is a set, so I've assigned the parameter set to be 2 bits of 10. And then, of course, flip is 2 bits of 11, 2 bits of 11. So then when we come down to the case statement, I can just say case, and this is for the least significant bit, J0, K0. So I have to do a J and K for each bit, because that's actually, I'm doing separate JKs here. Now, I could split this into 2 different always and split the bits up. I just did them all at once just because it was easy. Um, so I did a case on J and K. I've concatenated them together so it makes one nice thing. And hold, of course, keeps the value. S0 gets reback assigned to it. Reset, S0 gets cleared. Set, S0 gets placed a value of 1. And on flip, S0 gets not S0. Same exact pattern um, using J1 and K1 for the S1 bit. So I just literally copied this case through end case and set down. Now notice I haven't put a default in here. There really is no other case. When you're designing it, it could potentially get worried about it because there are the X's and everything else. Um, I think for readability, this is still quite worthwhile. These are the only options. For the stuff that we are designing, it is exhaustive. I could put a default in if I wanted, but I don't think it would be as readable as it is right now. So for my sake, I'm just putting it in this way and dealing with it. If I want to set a default, I would probably set default and then just put a separate thing for the reset condition. Just again, so I contain or keep the value to be nice and simple. Um, so anyway, that's that part of it. So really, this characteristic table is then used to define the flip-flop. Now, I'm not going to be doing, if you notice here, there's no next state, truthfully, because I actually just calculate the J and the K values. So there's no next state. All the next state stuff is built within the flip-flop itself. So this always at with the pos edge and neg edge is handling that. The assign, just like before, since I make my outputs a wire, I just assign the state to it. Now, you might be wondering, well, why not just make an output reg and then instead of having a state internal? That will work for some systems. Technically speaking, the Verilog standard, anything that is an output, you are not supposed to be able to read. So if you've got an output, you can't read it, and that's not good. Um, so that's how that one goes out, and that's why I do this, because this will work with every single system that's out there. All right, let me. So that handles the first part of our design. And the easy part is actually just what we did in the last video. Hopefully the last video you watched. We got these different Cardinal maps, and then we calculated these. All I now have to do is take those J's and K's for each one, J0, um, which is next state 0J, so that's J0, is S1 exclusive or in. So S1 exclusive or in. K0 is not that. And remember, you can put the not anywhere you want inside this sequence. I just put it in front. It just stands out as exactly not that. So it's easy to do. Um, for J1, right? So next state J1. J1 is S0 and not in. So J1, S0 and not in. Oops, I want to be highlighting the wrong thing. And then next state K1, K1, last one down here, is not S0 and in. So then we have not S0 and in. So you can see I just took the equations, translated into Verilog, stuck it in an always at star. If you remember, that is our combinational logic. So that's really kind of the idea here. Um, we've got the states and technically the input coming down. In our case, the next state logic generates J and K instead of next S. But same basic idea of that basic design. So there we go. Um, this is identical code. I literally cut and paste it from the other model. The only change I made in the whole thing was to change, model one and then whichever one I wanted to just JK here. We could have really done this appending it to the other design, but I didn't want to change it partway through and confuse people, so I just kind of copied this one and then just wrote a whole new section over here for implementing it. But otherwise, this is identical. Since it's identical, we can actually use that feature to compare it. So I'm going to take this and run it. Boop, boop, boop. Okay, we get that. And then I have the previous design. You'll see they've got different letters, right? To FHF, right? And this one is the 5EVJ. That was the previous design. But we can compare the two. Now, I've shown Q clock in reset JK for the new design, and all the other ones had next state for the previous design. But really all we have to do is look at the Qs and make sure they're the same, right? So they both start initially X, become 0, you can see 1 all the way down, and you can just compare them line by line, and they get identical values, right? At time 100, they both turn to 1s. Right, at 110, they both go to 2. So you can compare them, they're identical all the way down. That lets you see that the designs accomplish the same exact output, because all we matter is on the same input, and you can verify they're the same input. For the same input, they get the exact same output for as long as it's running. And that's what we care about, right? That we get that same functionality. So therefore, we have been able to verify that our new design is actually indeed working. And you can compare, look at the values of J and K and make sure they do it. But um, easy enough to see the input outputs are identical, therefore we're good. So hope that helps. You're welcome to play with the code. So you can see here's our new code. You can play around with it and see what you want. You can check on the other one. We've still got the old code is still accessible to you, which has the different versions of it, right? The RTL version, which is pretty similar to what we just did. Note the difference being that instead of that case statement down below, we've now got kind of a case statement that's built into our system for the flip-flop. So, um, so the flip-flop is more complicated when we come to the new system, but that makes the actual regular functioning part of the system, the next state logic, becomes much simpler. Anyway, welcome to read it. I do highly encourage using parameters when you do these because it's just a lot more readable. All right. Well, hope everything's good for everybody and you're staying safe during COVID. Bye.